Questions? Questions? Yes?
Do you know of any introductory texts that give a treatment of topologies as finite information mappings, like you're talking about?
I can tell you later.
Okay.
Okay. The enumeration operators are very well described in Hartley Rogers' book on recursive function theory, and I shouldn't be surprised if he didn't mention something about topology there, but I can give you some references later. Yes?
Are there any assumptions about F?
No, any set. Any set F, any set X. Any set, by means of Girdle numbering, could be conceived of as a lookup table. Any set X can just be thought of as some set. And how do I know a set? By finding more and more finite subsets of it. Other questions?
You're basically pairing.
Say again?
So this is basically pairing the inputs with the outputs.
Yeah, the input is X. I have to learn more and more about X.
Yeah.
And every time I learn something about X, I say, Mr. F, can you tell me something about the output? Sometimes he says yes, and sometimes he says no, okay? So when he says yes, you're able to then tell more about the output. But you may need to get more and more about X to get more and more about the output. That's how an enumeration operator works. Other questions? Wait, in the back here.
So topology is defined as the open sets are defined as basically possible sets containing a number of finite.
Well, open sets are unions of neighborhoods. So let me draw a picture to show you what an open set looks like.
Okay. So the neighborhoods generate.
The neighborhoods generate the open sets. Okay, so first of all, let me draw you a picture. The power set is a Boolean algebra. Everybody knows that as a picture of the four-element Boolean algebra, right? 0 element, unit element, and 2 complementary elements. That's the 4-element Boolean algebra. The power set is an infinite Boolean algebra, and I can't draw a very good picture of it. I'll draw the power set like this, of which the empty set is down at the bottom and the whole set is up at the top. That's a picture of the power set. Okay, and now what an open set looks like is this. You take the union of a whole lot of neighborhoods here by giving finite subsets of the integers and taking everything above them. And so a union of many neighborhoods, infinitely many neighborhoods, is a typical open set. I can't hear. Oh, yeah. Definition of continuity is a nice exercise that any undergraduate should carry out. That a function is continuous according to the epsilon delta definition. The same is true on the real numbers. If and only if the function is such that the inverse image of any open set is open. And all you have to say is the inverse image of every neighborhood is open. Because it'll go over unions. Yeah. Other questions? You had a question?
Yeah, can you give me an example of a discontinuous function in this case?
Can I give you an example of a discontinuous function? Well, you see, these functions that are continuous are going to have a special property. Any two continuous functions will have the following property. If x is a subset of y, then of course all the information from x is contained in y. These continuous functions are going to have the property that f of x is contained in f of y. Because if you're enumerating from finite subsets, whatever you do in x is going to be there in y, so you have to give that output as well. So all the continuous functions are monotone. Okay? What's an example of a non-monotone function? Complement, negation is non-monotone. The negation of x is the set of n's such that n is not in x. And so, of course, complement is a non-monotone function, and so it's not continuous in this definition. And this is why we have to watch out for fixed points, because could you have a Russell set R that was equal to the complement of the Russell set? No, because you just have Russell paradox over again. So the fixed point property only applies to continuous functions, and the monotonicity is a key feature that has to be watched out for. Thank you for asking that question. Good question. Please.
So basically, the enumeration operators are just there to help you map both the input and the output, like how you could better understand.
Yeah, and the point is, you can define enumeration operators in lots of weird ways. So we want to figure out how complicated can an enumeration operator be, right? But it's an input-output thing working on finite amounts of information at a time. Other question? Yes?
So where did you get the 3n from?
I'm sorry?
3n? Or, yeah, is that 3n up there?
Where?
Wait.
No, that's not three, that's X.
Oh.
What?
So, okay.
Where did you
so
see a 3?
The e.
That's the existential quantifier, for Kevin's sake.
I know. I know. Now I know.
Okay. No,
Okay.
Yeah.
So, and the dot still means that n and m are an input to x star.
oh, the dots here, I haven't gotten to the dots yet.
Oh, okay. All right.
Okay.
All right.
The upper dot.
Okay.
The upper dot.
Upper dot is just a separator.
Yeah. So n and m are inputs to x star, right?
I take n in x star such that the pair nm belongs to f. Does there exist a finite integer n in x star such that the pair nm belongs to f? Okay?
Yeah. Thank you.
So the enumeration operators are the continuous functions. I hope it's clear that this definition of f of x is continuous function simultaneously in f and x. A finite amount of information collected into f of x would only require a finite amount of information about x and, obviously, a finite amount of information about f. So application is a continuous function. Now, I'm going to reverse the definition of application to define abstraction. The problem of abstraction is, if you give me a continuous function, does there exist a lookup table that will simulate that continuous function? Given a continuous function, and I've just stated it here very loosely here by double dots here, given a continuous function of x, is there a lookup table that replicates the continuous function I'm thinking of? Well, just to be generous, I'm going to throw in the number 0, which is not an ordered pair, so I'll tell you why I did that in a minute here. But what I do is I say, okay, that continuous function can be applied to many finite sets. Do it. What is the value of that continuous function on a finite set? And you say, oh, it's a set. Yeah? Well, what elements does that set have? So I collect here for all possible finite sets that I can put in for x. I collect out the elements of the result of evaluating that continuous function on the finite set. And by recording that into pairs, I really have all the information you need to know about the continuous function. The continuous function I'm thinking of here is, of course, the function that goes, the continuous function that goes from x to blah of x, whatever that is there. I'm thinking of a continuous function like that. So if I just collect together the finite pieces of information about that continuous function, I have a lookup table that will give me the continuous function back again. So here's the key thing. I'm just using sets of integers, but to specify a continuous function, you only need a countable amount of information. The power set of the integers by Cantor's theorem is uncountable. But if you think of continuous functions, a continuous function can already be captured by just a countable amount of information. The same is true in the real numbers. The real numbers are uncountable, but the continuous functions on the real numbers are just of the same power of the real numbers, because a continuous function is completely determined by what it does to the rational numbers. And each rational number results in a real value, so altogether there are only a continuum number of values needed to specify a continuous function. Cantor's theorem said if you take arbitrary functions from reals to reals, you have a higher cardinality. But if you take continuous functions, you don't get beyond the cardinality of the continuum itself. We're doing the same thing here, only with a simpler topology. Okay? So enumeration operators are these things I'm thinking about when I make a continuous function and apply this abstraction operator on one of the variables. If it's continuous in all the variables, and I abstract out a variable here, I get a function on the remaining variables. It's an easy exercise to see that continuity is preserved there. And the way that I have defined lambda x, phi of x, is it's the largest lookup table that gives the behavior of the continuous function. And so that's why the axioms are going to be satisfied. That's why the axioms are going to be satisfied. Of course, the definition of reversing things to make the lookup table doesn't depend upon the notation x and y there. But the key thing is, lambda is defined as the largest lookup table that gives you the right values. And so that's why that equation is satisfied. Question?
Why did you limit 0 and 0?
So I would get the largest lookup table. You see, in a lookup table, 0 is never used, and so it was just a afterthought saying, oh, I never use 0. Some people could enumerate pairs so that 0 was included. I took an easier one there, so I had to throw 0 in there so I'd have the largest lookup table that gives you the right answer. And 0 never comes out in trying to figure out what the enumeration operator is going to do, because it's just not part of the lookup table that you need to invoke. Okay, and now you see what happens here with the eta abstraction here is many lookup tables can give you the same function. So this is the largest lookup table that gives you the function you're thinking about, but other lookup tables could give you the same function with less effort there because there's a lot of redundancy that goes on in there. So therefore, you have this principle here. This is a weakening of eta here that says lambda x f of x is very good here, but it may contain a lot of redundant information that you really didn't need to use in order to determine the continuous function we wanted to determine. How are we doing here? Yes?
So a lambda is a pure function.
What?
No? But we got lookup tables. But maybe I'm jumping ahead of myself. It's not. It can be an impure function as well.
What's an impure function?
Where for each input there's only one output that.
No, don't think that in terms of that term.
Oh.
You're so stuck on ordinary finite inputs and finite inputs. Wait. Let's not make fun of him. Think in terms of many-valued functions. These enumeration operators are many-valued functions. I could think of a lot of single-valued functions on the singletons, and I will want to think of singletons here. I could think of lots of functions such that if I apply it to a singleton, I give a very nice singleton out as a value. And so all the ordinary functions from integers to integers could be construed this way. But our enumeration operators you should think of in terms of many-valued functions. So the output, y here, is all the things you can get out of the input n. This is very little input, but whatever the lookup table is, you might get lots and lots of output out of it. Okay? Does that make sense?
Yeah.
Think in terms of many-valued functions.
Okay, yeah, that makes sense.
Okay? So that's the model. And that's the consistency proof for lambda calculus. Because, of course, there are many, well, let's go a little bit further. There are many different functions, but there are many different functions that you can define just by pure lambda terms, so we'll need to think about that. Okay. Now, here is the annoying thing. Often at 3 o'clock in the morning, much to my wife's consternation, I kick myself in the butt. I was a graduate student in Princeton in 1957. I got my degree in 58. I knew about combinators. I knew about lambda calculus. Church was disappointed in lambda calculus and never spoke to us about it. Many of the students asked him, won't you lecture on lambda calculus? He always refused because of the inconsistency of his logical axioms. Not these equational axioms, when he wanted to add quantifiers and things to the lambda calculus. I knew about the lambda calculus. I'd studied Kleene's books very, very carefully. Kleene came to Princeton in 57 when Church was on leave. I got to be very good friends with him. Earlier, John Myhill, I knew very well from California when I was an undergraduate there. And John Shepherdson had come to many conferences. I knew him too, English logician. And they had set themselves, you see, Kleene introduced partial recursive functions. And so Myhill and Shepherdson thought, how can we think about partial functionals mapping partial functions to partial functions? How can I go up one level from the partial recursive functions to the computable partial functionals? And so they wrote a very nice paper about it. Almost simultaneously, Hartley Rogers, lecturing at MIT, had Richard Friedberg as a smart Alex student there, and Friedberg came up to his solution to Post's problem of giving independent post-Turing degrees there. But one of the things they did together, and it's reported in Hartley Rogers' book, was actually published later, but they had abstracts on it, and Hartley Rogers came to Princeton to lecture. I got to know him. They introduced enumeration operators. Enumeration degrees, the idea of a degree is, we say, in terms of enumeration operators, B is reducible to A by means of an operator F if from A you can get B there. Now, Rogers and Friedberg said, let's take these enumeration operators given as recursively enumerable lookup tables. Those are the computable enumeration operators. So the enumeration degree of sets are when this is recursively enumerable here, a fixed recursively enumerable set, then we say B is reduced to A if that enumeration operator can recapture B from A there. You wouldn't believe it, but there are thousands of papers on the structure of enumeration degrees. The lattice of enumeration degrees is horrible. It's very complicated. The lattice of Turing degrees is horrible too, and it's related to this. Turing degrees means you not only have to reduce B to A, but for a Turing degree, you have to reduce the complement of B by some other process to the complement of A. Those are the Turing degrees. And Friedberg got his fame by proving they're incomparable Turing degrees. Besides recursive and everything, they're intermediate ones and incomparable ones. They have a horrible structure too. But here is the thing that why I kicked myself in the middle of the night. Friedberg and Rogers defined application, and Myhill and Shepardson essentially defined abstraction, where they wrote in their papers by saying, wow, look at all the interesting operators we can obtain by very simple formulas. If only they had thought of it, they had a general process of abstraction. Nobody said, do these operators have any algebra to them? Do they have equations relating one kind of operator to another? I could have thought of this in 1957 and I would be rich and famous now. I don't care about famous. I could have done it in 57, and I'm trying to tell you I could teach this to juniors. If only, if only. So here are some properties of these things here. So first of all, lambda abstraction works very nicely. If one function is giving you constantly over all the possible inputs less information than another function, then the first lookup table is a subset of the second lookup table. Also very easy to prove. Also, if you take a pairwise intersection of continuous functions, you can just take the intersection of the lookup tables, corresponding, and similarly with union. So there are many interesting laws here. This is going beyond lambda-calculus because I'm invoking some quantifiers about the overall behavior of functions, but I'm also using the inclusion structure. Like I talked about monotone functions, I'm also using inclusion, not just equality there. So there are many interesting properties. And now the key thing is that a continuous function will be regarded as computable, and of course Friedberg and Rogers only looked at the computable ones, and they only thought of the functions of one argument basically there, but you could think of functions of many arguments where if you abstract out all the variables, that would be a gigantic lookup table with looking at results of results of results inside there. If that lookup table is recursively enumerable, that's a good definition of saying the enumeration operator is computable, because we'd be able to set up something in terms of recursive functions to enumerate the lookup tables to do all of that. And that's what we mean by computability. So computability here is on the same plane as recursive enumerability. So that's the definition. Now, in terms of fixed points, it's an exercise, but needs to be checked out there. All the pure lambda terms define computable operators. Let's go back and look at the definition of application there, and you'll agree with me. I could think of arbitrary lookup tables and arbitrary sets there, but if I'm thinking in terms of recursively enumerable sets, if I can recursively enumerate x and recursively enumerate f, then I can recursively enumerate f of x. What?
Can you define recursive enumeration again, please? Sorry.
Yeah. Recursive enumeration can be defined using the most basic kinds of recursion, and primitive recursion is an extremely good one. And so primitive recursion, you can think of it as syntactic analysis. You take Girdle numbers for proofs or Girdle numbers for inputs or something like that. You take this fixed recursive function to it and find out what you can get out of it. And if you can get out of something good, you put that into the output. So you think P of n, it's this thing I wrote down.
And something good is the terminal condition?
And I indicated terminal conditions in the simplest possible way of being positive there. So P of n equals 1 plus m. Okay? So 0 means failure, and positive means success. And then you read off from success what you won in the lottery.
Cool.
Well, Girdle knew it very well back in 1931, 32. Okay, so that's what recursive enumeration will be, and what I'm saying is that these things are such that if the f and x are recursively enumerable, then f of x is recursively enumerable, but also if your continuous function you're thinking about here is computable, then you'll be able to enumerate the lookup table there. So anything you can write down in the notation of lambdas and application purely without any other things in there has got to represent in this model a recursively enumerable set. Just because the basic operations preserve recursive enumerability, so any amount of compounding of them preserves recursive enumerability. Doesn't it make sense? Okay. So the next step is to see how far we can do this. And so it turns out to be a little more complicated, a little bit more complicated, but still based on very, very basic principles to show that not only does every continuous function have a least fixed point that can be defined in lambda calculus, but also, because it's defined in lambda calculus, the least fixed point of a lambda operator is of a computable lambda. The least fixed point of a computable enumeration operator is computable. Here's another way in terms of least fixed points. Least fixed point of the continuous function of f is just the union of the iterates f of f of f of f of f of f on the empty set there. That's also an easy way to find least fixed points, and it also shows you if f is a computable operator, then of course you can compose computable operators together to get more computable operators, so you can keep enumerating all the junk. So therefore the least fixed point will, if f is a computable enumeration operator, the least fixed point of f is recursively enumerable. Question?
Yeah, so isn't it kind of close to the existence of free monad and the conditions for the existence of free monad?
Yeah. We generate free structures just by enumerating things over and over again and putting in only what we absolutely have to put in, no more nor less. Yeah, so it's very related. So therefore you can, in terms of Girdle numberings, you can set up all kinds of defining structures as sets of integers where the Girdle numbers are telling you what kind of expressions should be in your set. And so all kinds of things can be set up here. It's all related. Other questions? Please.
I apologize in advance because I will blunder my way through this question. But if we have an expression, a lambda expression that is partial recursive expression, meaning that it diverges and never terminates.
No, don't think in terms of divergence and all of that. Think of enumeration, saying you can only achieve what you can positively achieve. Don't look at what you can't achieve. You can't figure it out. Only do the positive part. That's the way the enumeration works. They only say what you have to get work with, you can get stuff out of it, and that's all you can do.
Okay.
Of course, you can take complementation and things like that and ask your questions. What are the complements could give you and other things like that. But that's not part of the original concept of what an enumeration operator is. And now the computable ones are the ones where the evolving of the output can be achieved by means of a recursively enumerable lookup table. So you can't just use an oracle to answer your questions. You have to really slave to use the recursive enumeration to get the information that you need. Okay, so that's the difference between arbitrary sets and sets that can be unfolded in a computable way. Other question in the back there was another question. Okay, so let's, yes.
Can you repeat what the pure lambda kind?
Yeah, just in terms of the syntax of lambda abstraction and application. You only use of and lambda. Okay, so think of all possible expressions. I should have mentioned some interesting expressions here. I did mention them. We'll take a break soon after this here, but let me write this down here to answer this question. K is lambda x, lambda y x. That's a pure lambda expression.
So what would be non-pure?
What?
What would be a non-pure?
If you stuck in a constant of some crazy subset. In our universe here, we have all possible subsets of integers, and there are a lot of insane ones. Okay, so if you put in a constant, it's bringing in something external.
So the smallest set which I get by doing application and
Yeah. Now for S,
gives me the pure.
here's another pure one. I'll have to write it down here. That's a pure lambda expression, and that's the combinator S. What?
That's only the F and G are pure themselves.
No, those are variables. You can use any variable you want.
So basically you mean no free variables?
I'm sorry?
Okay, got it.
No
expression. So
Well, okay. If you use free variables, then you're thinking of the whole thing as being a continuous function of the free variables. And so if you take, and what I'm saying is, these have no free variables, so therefore what I've called K and S are recursively enumerable sets by what I said there. But you could take free variables in there and write lambda x f of g of x as defining the composition of f and g. So that's a pure lambda expression with variables in it, and it defines a binary enumeration operator, which is computable. A pure expression has variables, lambdas making bound variables, applications making longer expressions. any pure expression gives you a continuous function of the free variables, which is computable in the sense of recursive enumeration.
Can you say that again, please?
No, why don't you think of it again? I'm going to take a break now, but if you want to come and whisper in my ear, I'll tell you. But let's take a break.
Okay.
In the extra references that I gave you in my one paper there, I give the proof. Well, first of all, I erased it here. That infinite union there is the easy proof that any continuous function has a least fixed point. Okay? But I had to take that infinite union to get to it. It turns out in the lambda calculus, if your continuous function phi, you can write down in the lambda calculus, even if it has some extra parameters in it, doesn't matter. If you take that self-application and apply the self-application to itself, I calculated that in the first session there, just with combinators. That gives you a fixed point. You see, first you do a self-application. The nobler there is take lambda x, phi of x of x. So this is the crazy thing, where functions can be applied to themselves as arguments. Well, let's just try it and see what happens. Okay. I make that abstraction there. I know that that's well defined in the model because I'm using continuous functions and application, and it's all allowed in the model. Now apply that nobler to itself and just use beta reduction, the basic axiom of lambda calculus, and you'll find that P is equal to phi of P. Look, nobler, nobler. If we call that P, then if you stick nobler in for x, you're going to get phi of nobler, nobler. In other words, P equals phi of P. The pure lambda calculus allows you immediately, via self-application, to define a fixed point. Now, I wrote it out in one of the papers that's in the collection of background things there. There's a very nice proof that it must be the least fixed point. And the reason is that in the Girdle numbers I used, the Girdle number of a pair is always much larger than the terms of the pair. The Girdle number of a finite set is always larger than the elements of the finite set. So in other words, when you go from Girdle numbers of compound finite structures to their components, you're always getting smaller numbers. That's a well-foundedness principle. It says as you keep taking components of components, in a finite number of steps, you'll get to 0. You always get to the bottom in a finite number of steps. That well-foundedness of my Girdle numbering can be invoked directly to show the crazy lambda calculus self-application definition necessarily gives the least fixed point. We don't have time to go over the proof here together, but I wrote it out in one of the papers you can find there. Okay? So lambda calculus allows you to notate least fixed points. But maybe least fixed points are very closely connected to recursion. Let's start bringing in, besides lambda calculus, let's start bringing in the integers. Well, as a multi-valued function, the successor of the set X is just the set of successors of its elements. Have to think in terms of multi-valued functions here. The predecessor means subtract 1 from all the elements. Okay? And now we can also make a test here we can test Z for containing 0 or not containing 0 there. And if it contains 0, we output X. And if it contains a positive element, we output Y. But in the multi-valued way, if you get both answers, then we take the union of X and Y. But everybody can see that these are continuous functions, and they must be computable continuous functions, because it's so easy to go from information about X or Y or Z to what is output. Those are 3 examples of enumeration operators, continuous, computable. And now the key thing here is all computable continuous functions can be composed by using lambda calculus and arithmetic. Arithmetic gives you the possibility of analyzing Girdle numbers as other kinds of structures. The lambda calculus only uses a fraction of the power of Girdle numbering. But if you do full arithmetic that you can do in terms of iteration from successors, predecessors, and testing for 0, then you'll get all recursively enumerable sets. So now what I say is we can set up a computable function, and now it'll have to be a multi-valued function. I'm only showing a little part of the function here of how the function will operate on single integers in terms of singleton subsets. Okay? The number 0 is made to correspond to the combinator k. The number 1 is made to correspond to S. 2, 3, and 4 do arithmetic. Larger numbers fall back to earlier numbers and apply one to the other. So in terms of what number I put into this universal process V here, I will do the combinators and the arithmetic over and over and over and over again in many ways as possible. Now, you really have to go back to the definition of primitive recursive functions and recursively enumerable and show how to represent that in lambda calculus, and then you have to check that you'll be able to get a recursively enumerable set from a primitive recursive function in terms of this process. And so it would take a whole lecture to go through the details of that proof. But in fact, the basic operations of lambda calculus and arithmetic, when done over and over again, give you all recursively enumerable sets. So I agree. I haven't proved it here for you, but I'm telling you it's a good thing there of that. Now, where's my other thing here? I didn't put it in the notes here. Okay, so let me put it up here. If I take this universal process of doing everything in the notation, including successor, predecessor, testing for 0, over and over again there, not only will I get all recursively enumerable sets eventually, in other words, the n will eventually be a Girdle number of some recursively enumerable set, and every recursively enumerable set will have a Girdle number. And that's what you need to check out by going back to that way of thinking in terms of RE, in terms of primitive recursive functions. However, we can also think of doing these computations with resource-limited means. Suppose you say, you can't use arbitrary Girdle numbers, you can only use the Girdle numbers that can fit inside the state of Colorado. Okay? So you would get only a finite approximation to what you can do if you limit your Girdle numbers. So here's a notation for limiting Girdle numbers here. B sub k means limit your computations to those Girdle numbers, k for Colorado here, that are limited to Colorado. Okay? And that's for the basic things here. But for the larger ones here, of course, you take these finite approximations applied to the finite approximations. The definition of application is such that a finite set as a lookup table applied to a finite input does only give you a finite amount of output. So everything stays finite there. So these are finite approximations to the computations, and you can think of it as a kind of resource space limitation. Here, it's a very crude kind of complexity of just taking only a few Girdle numbers that can be used. However, if you use more and more and more and more Girdle numbers, you'll eventually do everything you can there. So, V is the universal enumeration of recursively enumerable sets. It's the analog of the universal Turing machine, and it's much quicker to write down. I hate programming Turing machines. I just hate it. Even Turing himself made a number of mistakes in his original paper that had to be corrected later because the programs are hard to write because of the very limited means of running back and forth on the tape to do Turing machines. But this is much less to write down, and we can use these resource approximations here to show how to get recursively enumerable and separable sets. We can say they're the lovers of 0 and the lovers of 1 here. The lovers of 0 are the such that there exists a Girdle number such that this diagonal computation gives you a 0 before it gives you a 1. 0 is loved, it comes up earlier, and that's what I put in L0. Whereas 1 is loved if the other way around, 1 comes up first before 0 comes up. And so those are two disjoint sets. They're clearly recursively enumerable because I only have an existential quantifier here. And it's quite easy to prove. And it's the old trick that Barclay-Rosser found an improvement of Girdle's incompleteness theorem by using a trick for self-reference there, where you ask, I get to something before you get to the opposite of something. That was Rosser's trick. So this is just an application of Rosser's trick to give two disjoint recursively enumerable sets, which are recursively inseparable. So again, I think in this notation of lambda calculus and using it as a basis for recursion by means of the fixed points, we get the benefit of universal Turing machines, I think, with easier to follow notation, but that's my personal opinion on it here. So that's that. Let me go on here now. Okay, so lambda calculus plus a little bit of arithmetic iterated over and over again gives you all of basic recursion theory. What I want to show is that we can get more out of this here by looking not just at the whole model, but by looking at submodels, by filtering out to look at just certain of the elements of the model. I have a model for the lambda calculus which contains arithmetic and therefore contains recursion theory. And we can think of all computable recursion operators this way. But we can also look at submodels with some closure conditions on them. So a very basic idea of closure, and in algebra and in logic we use it all the time, a closure operator. Typical closure operator is to take a subspace of a vector space, you give some basis vectors, and you take all combinations of the basis vectors, and that gives you a subspace of the whole space. Or you take an algebraic structure like a group, and you just take some elements of the group, and you close that under the group operations, and you get the subgroup generated by them. Or a very popular one is logical deduction. You take some logical principles for proofs, and you say, take some statements as axioms and close the axioms under logical deduction to get everything that can be proved from the axioms. So in an abstract way, closure is something, and we can express it nicely in the lambda calculus, thinking of the integers again as Girdle numbers, say of expressions or other things like that. A closure operator is an operator such that from the generators x, you expand it to the closure of x, but once you've done it once, you don't have to do it twice. In other words, things that are provable from things that are provable or were already provable. So a closure operator is such that, and we could even say that in lambda calculus there, we could say that the identity function is contained within C, which is equal to the composition of C with itself. And very shorthand. Now these closure operators, they're more general closure operators. These closure operators have a finitary property that a finite number of conclusions requires only a finite number of assumptions. That's true in logical deduction based on that. Question?
The closure operator sounds a lot like a fixed point to me.
Well, the closed elements are the fixed points of the closure operator. And a closure operator can have many fixed points, and it's such that this thing here, if I take an arbitrary assumptions and take the closure of it, that is closed. Once you closed it, it's closed. Right? That's what closure. And so there's so many familiar examples that come from things like algebra and logic and as I say, finitary notions that in order to get a finite amount of information about what's deducible from the axioms, you only need a finite number of axioms to do that. So that finitary property is important. So these closure operators and also the closed elements here, the closed elements of the closure operator form a nice lattice. In fact, they form a complete lattice. I really don't have time to go into lattice theory here. Power set of n is a complete lattice because we have that inclusion operation and we have arbitrary intersections and unions of power set. It's a complete lattice. The closed elements of a closure algebra form a complete lattice, and you have to be a little bit careful about what the least upper bounds of families of elements and the greatest lower bounds of families of elements are there. The greatest lower bounds just turn out to be the intersections, but the least upper bounds, you have to throw in an extra closure to get it there. But the fixed points of a closure operator also form a complete lattice, which is analogous to the power set. Only the power set is simpler in its lattice properties because it's a Boolean algebra generated by the singletons. And other lattices are less like Boolean algebras. But lots of them can turn up as countably based things from closure operators. Now, if you have two of these lattices, you can map from one to the other if you have a continuous function which will go from one to the other. So it's very easy to write in lambda calculus here a continuous mapping from the fixed points of C to the fixed points of D is such that if you give me a fixed point of C, I will apply F to it, and then if you allow me to clean things up by closure under D, I will get a fixed point of D. Let me write it on the board here. This will give you the mapping from the closed elements of C, and this is just an enumeration operator, but I'm letting it to stand for all of its fixed points. A mapping from the closed elements of C to the closed elements of D is just such that it's an enumeration operator such that if you coerce an arbitrary input into being a fixed point of C and then let F operate on it, it won't do anything too horrible to it because you can coerce that into being a fixed point of D. So it will certainly follow that every fixed point of C becomes a fixed point of D. And in fact, on these lattices, you can take the analogy of the power set and make the fixed points of C a topological space, and the lambda calculus gives you a notation for all the continuous functions between those lattices. So you see, the Girdle numbers give you possibility of thinking of any kind of finite structure. But now you can look down and specialize the structure in special ways. And so these closure operators give you a way of doing a lot of that.